Okay, this is applications of exponential equations, part 1. And I just don't want the videos to get too terribly long, so I'm splitting it up into 2 parts. But I think there's only one worksheet that goes with this. So when you are, this is called the growth and decay model. And there's different forms, but this is the form that I like to use that has the base E in it. And it's basically A of t, the amount of whatever at time t, is equal to A sub 0, the initial amount of whatever, which it could be people, it could be bacteria, it could be radioactive material, it could be money, the initial amount of whatever, times the base E, the number E, raised to K times T. K is known as the growth or the decay factor. It's known as a growth factor if it's positive, it's increasing, or decay factor if it's decreasing, getting smaller when K is negative. Okay, so that's the whole, this is the model we're going to be using for every exponential situation. So on our sheet, we have a few different things. So the number 3, or the first one on your sheet, it says, a certain paint from the Lascaux caves of France, I don't know if I said that right, contains 15% of the normal amount of carbon-14. Estimate the age of the painting. So this is an illustration of how we can use a decay model, an exponential decay model to figure out how old something is, carbon dating. So what I will always give you is the decay rate of carbon-14, which is what we need to do this problem. So for number 3, we got to know that we're dealing, that the decay rate, because this is a carbon dating problem, is equal to, for carbon-14, is negative 0.000121. That's the decay rate for carbon-14. Okay, I will give you that. That's given. So it says a certain paint from these caves contains 15% of the normal amount. So, in other words, after some time has passed, how much is there? 15% of the original amount. Or of in math means multiply. So, and if we change this to decimal, how much is there after some time has passed? 0.15 of the original amount. A sub 0 is the original. So that's how much there is after some time has passed. So the question is, they said, how old is this? How much time has passed? That's what we're trying to figure out. So this is always what we're going to be using. So what they told us here basically was A of t. So that is 0.15 A sub 0. This is the amount of carbon-14 they found in it when they found it. They're like, oh, this is how much is left. Is this equal to the original amount? A sub 0. We don't even know what the original amount was, but it doesn't even matter. We can still solve this without knowing that. Times E raised to the KT. K for carbon-14 dating is negative 0.000121 times T. So to find out how old this painting is, or how old it was at the time it was found, we can solve for T. How will we solve for T? Recognize this is an exponential equation. And then you say, how do I solve exponential equations? Well, first, I isolate the exponential expression. So get this e to the whatever by itself, then apply an inverse or a logarithm. So let's do that. Let's isolate the exponential expression by dividing both sides by a sub 0. So what we get here is 0.15 is equal to e to the negative 0.000121t. Now, to solve this exponential equation, we introduce an inverse or a logarithm, and what I'm allowing us to use is log base e, so this is going to be really nice. Let's apply the natural log to both sides. All right, what we have here is log base e of 0.15 is equal to log base e of e to the power. These are undoing each other. So basically, we have the natural log of 0.15 is equal to negative 0.000121t. This is turned into a linear situation. Now I just simply divide both sides by this, and I'll get that t is, let's see, the natural log of 0.15 divided by negative 0.000121 gives me 1, 5, 6, 7, 8, 9, 1, 5, 6, 7. If I round to the nearest year, it's approximately this many years old when it was found. So that's how we can do number 3. Okay, the next one on our page is about radioactive decay. So let's have a look at that. We are particularly interested in radioactive decay, well, for many reasons, but of course to keep ourselves safe and to contain harmful substances in a way until they are non-existent. So they can take really a long time to decompose, and sometimes they're used in medical tests, like they might inject you with a little bit of radioactive material so that you will glow in the right places wherever your system's active. And so those have a very, very fast decay rate. So they're used in all kinds of applications. Let us read number 6. This is a terribly sad thing that happened in real life. Radioactive cesium-137 was emitted in large amounts in the Chernobyl nuclear power station accident in Russia on April 26, 1986. The amount of cesium-137 remaining after X years in an initial sample of 100 milligrams can be described by this. So let's just stop right there and write this equation down. They gave us A of X is equal to 100 E raised to the negative, oh my goodness, I cannot see that number, negative 0.012295. Negative 0.012295 X. I don't know if I wrote down the right number, so we're just going to go with this because that's what it looks like. Okay, so it says, let's just discuss this. It says the amount of cesium-137 remaining after X years. That's what A of X gives us. So instead of T, they have X is the number of years. That's fine. After an initial sample of 100 milligrams. 100 is the initial amount, 100 milligram. That's a very tiny amount of this. So we're going to see why it was so destructive in this accident. It says estimate how much is remaining after 50 years in this initial 100 milligram sample. So let's do that. How we would do that is say, well, how much, this is the amount after some time has passed. So we want to know, for part A, how much is left after 50 years has passed. So we would just put in 50 for X. E to the negative 0.012295 times 50. So let's estimate that. Just put that in your calculator. 100 times E to the negative 0.012295 times 50. And 54, this is 54.1 milligrams are left after 50 years. Okay, let's just think about how destructive this accident was. After 50 years, 100 milligram sample has not even decayed to half of that amount. That is a long, just caused a lot of damage because there was a whole lot more than 100 milligrams in that accident. Okay, so then let's see here. It says part B, we're still on part A. It says, estimate how much is that? Okay, so it says, do you think, is the half-life of cesium-137 greater than or less than 50 years? Well, after 50 years, it had not even decayed to half of that much. So I think the half-life, by the way, half-life is how long it takes for a certain amount to decay to half of that amount. That's what it is. So, what is half of 100? Half of it is 50. So the half-life of cesium-137 is the amount of time it takes for 100 grams to decay to 50 grams. Or the initial amount doesn't matter. What if they started with 700 grams? Well, the half-life, that same amount of time would be for after that half-life, 700 grams would have decayed to 350 grams. So the initial amount doesn't matter. It's how long it takes for it to decay to 50% of the initial amount. That's half-life. So in this case, we wanted this 100 milligram sample to decay to 50 milligrams. How long will that take? It's going to take longer than 50 years, because after 50 years, it had only decayed to 54 milligrams, not 50. So it's going to be a little bit longer than 50. Let's see. So part B, it says estimate the half-life. So let's figure out the half-life. So this is one way you can do it. This is what the working equation. We want to know how long it will decay to half of this amount. We already said half of 100 is 50. So we'll say 50. This is how much we want to have. 50 milligrams, right, is equal to 100 milligrams. And you don't have to write the units. I'm just emphasizing this is what we're interested in. Times e to the negative 0.011295. No, 12295 times x. So this is how I'm setting this up. I'm solving for x. How long will it take for this to turn into just half of that? I isolate the exponential expression by dividing both sides by 100. 50 divided by 100 is 1/2. That's not coincident. That's because we want to know how long it would take to decay to half of the initial amount, is equal to e to the negative 0.011295x. Solve for x by applying a logarithm. The natural log of this is equal to the natural log of that. Log base e of e to the whatever. These undo each other. So basically we have the natural log of 1/2 is equal to negative 0.011295 times x. I will divide both sides. 0.011295. And that will give me what x is. So let's figure that out. Let's put it in our calculator. The natural log of 1/2 divided by negative 0.011295 gives me 61.4. So it would take 61.4 years for this sample to decay to half of the original amount. So that's its half-life. Okay, let's do number 5. And then we will call this video over. So, let's see. Number 5 says, it's the half-life of radioactive lead. It says, the half-life of radioactive lead-210. So here, when you read this problem, lead-210 is the name of that type of lead. The 210 is not a number we're going to calculate with. Okay, so the half-life of radioactive lead-210 is 21.7 years. The half-life is 21.7 years, okay? And then it says find an exponential decay model for this. So we have to find this model. So a model counts when we know the decay factor. So this is what they told us. So we could have done this in the previous problem as well. Put in a sub 0 for the initial amount instead of 100. It still works if you don't even know the initial amount. So that's what I'm going to do here. My job, they told me this much information, and I need to find K to be able to write that model. So this is what I'll do. For this lead-210, it takes this long for it to decay to half of the original amount. 1/2 of the original amount is this. This is how much I have after this much time has passed. So I'm going to write this. I don't know this. How much I have is 1/2 of the original is equal to the original a sub 0 e to the k. I don't know k, but I do know the time, 21.7 years. I'm going to solve this equation for k this time, and that will be the decay rate of lead-210. So let's solve this. Isolate your exponential expression. Get him by himself by dividing by a sub 0 on both sides. So when we do that, divide by a sub 0, we get 1/2 is equal to e to the 21.7 times k. I'm going to apply a natural log to undo the exponential, the inverse. Take the inverse. So I'll say, okay, natural log of 1/2 is equal to the natural log of this. The natural log of 1/2 is equal to log base e of e to the something. These are undoing each other. I get 21.7 times k. I just need to divide by 21.7, and that's going to tell me what k is equal to. So let's round this to maybe 5 or 6 places. So in my calculator, I'm going to take the natural log of 1/2, and I'm going to divide it by 21.7, and I get negative 0.03194. 03194. I could also go on to 2. I'll go ahead and put the 2 on there. Now, job number 1, write the exponential decay model. It looks like this. A of t, this is for lead. I think that's PB. Lead 210, I'll just call it that. A of t is equal to the initial amount times e raised to the negative 0.03194 times t. This is part A, the exponential decay model for lead 210. Now let's answer a couple of questions. Estimate how long it will take for the sample of 500 grams to decay to 400 grams. The initial, so this is part A, okay. Part B says estimate how long. We're looking for time, t, that's what we don't know. How long will it take for t to, we got to solve for t, for an initial amount of 500 to decay to 400. So it goes like this. How much after some time has passed is going to be 400. What was the initial amount? 500 grams. E to the negative 0.03194 t. We're going to solve this equation for t. Isolate the exponential expression by dividing both sides by 400. I'm sorry, by 500. Then we get e to the negative 0.03194 t is 4/5 if I simplify that. Introduce a logarithm. Natural log equals the natural log. Log base e of e to the something. These undo each other. Is just, we get the natural log of 4/5. Is e to the negative 0.03194 t. No, these got undone. I'm getting a little bit tired apparently. Negative 0.03194 t. Now to solve for t, we will just divide by that number right there. This is what t equals to. So we'll put that in our calculator and we will see that it turns out to be, okay, the natural log of 4 divided by 5 divided by negative 0.03194 gives me 6.985, or about 6.985, or I'm just going to say about 7 years. Okay, for it to decay to that amount from 400 grams to 500 grams. So if we had to write a sentence, it would say, we would say, it would take approximately 7 years for a 500 gram sample of lead 210 to decay to 400 grams. So if you had to write a sentence, you would just write something like that. C, estimate how much of the sample will remain after 10 years. Of the 500 gram sample will remain after 10 years. So let's just do that. This is very simple. This one's easier than part B. How much is left after 10 years? C, how much is left after 10 years? This is our model. So we'll say, well, I don't know. How much is left after 10 years? We'll plug that in. The initial amount was 500 grams, right? E to the negative 0.03194 times 10. And we're just going to put this in our calculator. And so that would be 500. E to the negative 0.031942 times 10 gives me 363.3. 363.3 grams here's our sentence, of lead 210 are remaining from the, remain, not are remaining, 363.3 grams of lead 210 remain from the initial 500 gram sample of lead 210 after 10 years. So you can write a sentence if you need to that kind of talks about the whole situation. Okay, this is part 1 of our exponential models video.